Hello grade 12s, good to be with you today. We're going to do a really important section on chemical change. The subsection is called rates of reaction. You might also pick it up as reaction rate. Now this section is fundamental to so many other sections that it's really important that we lay a good foundation here and we take all the concepts that are interlinked and related, concepts of energy, concepts of reactants and products, concepts of a catalyst, concepts that relate to a graph so that we can use them in later sections. But I've put together a little checklist for you. Let's make sure that you've got this detail correct and that you understand this. Before you go, you're preparing for an exam, you need to have a checklist. Do I understand this? Can I do that? Well, let's have a look at our checklist. Here we go. Under reaction rates, you need to make sure you can do the following. You need to make sure that you can explain chemical reactions in terms of collision theory. Now, that's a really important bit of theory that you need to go back to. Make sure that you can engage with it. We'll have a little bit more to say about that when we come across questions that relate to collision theory, which we'll do just now. Now, the next thing that you need to be able to do is you need to be able to draw energy profiles to explain energy changes in a reaction. Some of this is work that you will have covered in grade 11, but we need to recall it now for our final exam. Now, the next part is also really important, and it's really rote learning, but we need to know what the factors are that affect the rate of a chemical reaction. Guys, you are going to get a question either asking you to state the factors or to apply the factors to predict what's going to happen if something changes. So you really need to learn those. Make sure you've got them sorted out and that you've got the checklist and you say, yes, I know all the factors and I can explain these factors in terms of collision theory as well. That's really important. The next two are really critical as well, and you'll see that in common exam papers. You're required to interpret different graphs that demonstrate the rate of a reaction, and often what has come up recently in exam papers, you're asked to describe the scientific investigation, and you need to be able to understand the process that's taking place in the context of reaction rates. So with that little checklist, hope that's reminded you of some key points. Let's go and have a look at some questions that have been selected from previous exam papers so that you can prepare yourself. As we're going through these, make a mental note. Yes, I know that. Yes, I know that. I've got the checklist all sorted out. If you practice in this way, you'll be sure to make sure that when you're faced with a new question in the exam, you can access the information that you've organized and stored in your memory to be able to get 100% on this section. It's really not impossible to do that. So let's go and have a look at the first question. And we're looking at question 1 here. It's taken from the November 2011 paper, and it's question 9 on that paper, but it's our question number 1. So what does it say? It says, study the following reactions. We're given 2 reactions. When you are given your exam paper, make some notes about it. So you've got reaction A, which gives you X plus Y goes to give you R plus S, and you're told that the delta H, the heat of reaction or the enthalpy, is minus, please make note of that, minus 200 kilojoules per mole. It also tells you the activation energy for the reaction is 350 kilojoules per mole. Now what about reaction B? Slightly different. Tells you it's C plus D, giving you E plus F, and at this stage notice that the delta H, the heat of reaction, enthalpy, is a positive value. Now in your head you should be, as you're reading that, you should automatically be thinking, I'm not even looking at the question, what can I interpret? I notice that there's a difference here. There's a negative delta H and there's a positive delta H. As soon as you see delta H, you must be asking yourself, what's this telling me? If it's negative, it's less than 0, which means that it is exothermic. So I'm going to write in over here, exothermic. And if it's positive, then it's going to be endothermic. So even though they might not have asked a question about it, I've written down this information so that when I do see the questions, I can relate to them and I'm not having to think minus, less than 0, positive. I've already made the link. I don't have to do that over and over again. So also notice here that the activation energy for the second reaction is 600 kilojoules per mole. And so this one requires more activation energy. The activation energy here is bigger. And you should just take a note of that as you're reading through. So you're starting to interpret. Now let's get into the question. The first question that we're asked over here is, are the above reactions endothermic or exothermic? Okay, so we want to recognize and we have to explain. So let's set it out very neatly and very nicely. What we're going to say is for reaction A, we recognize that delta H is going to be less than 0. So that means it must be exothermic. Now, to check that it is exothermic, we need to make sure that we understand what delta H is. A very good way of doing that is just sketching an energy profile to check that we've got it all clear as well. You don't have to do this in the exam, but I think it's a good just reminder for us while we're going through this question. So if I were to draw an energy profile diagram, I'm going to draw my axis over there, and this is going to be energy. And this is going to be the reaction coordinate. And what we have over here is the energy of the reactants. And over here, for this reaction, because it's exothermic, we're going to put the products over there. And we complete the profile by drawing in the loop over here. Now, I hope you can see that as a result of this, your delta H is represented by that difference there. The difference between the energy of the products. So what is delta H? Delta H is the energy of the product minus the energy of the reactant. The reactants are the things that we start with, the product are the things that we end with. So have a look at this and we take the values and see it clearly. When the products have a lower energy, these are lower, this is lower, and the reactant here is higher. So if we take the energy of the product minus the energy of the reactant, we're going to get a negative delta H. And I hope you can see as well, in this particular graph, in this profile, what makes it very clearly exothermic is the activation energy, the energy required to put in, is less than the energy that is released. This is the energy released. So that's why delta H is negative for an exothermic reaction. Hope you've got all that information and you can check it for yourself so you've got it very clearly. Now let's move on to the part B, because although we've done all of that, we didn't really need to do it for our answer. Right, let's write out for reaction B, what have we got? Have a look again at the information that is given. Remember that here the activation energy was given as 600, which is a big amount, bigger than the previously. But the important information, not the activation energy, but the delta H. And we recognize that it's positive, 150 kilojoules per mole. So what we're going to say, for reaction B, we've got the following. We've got delta H is positive. It's greater than 0. This means that it is an endothermic reaction. very quickly, remind yourself, what would the energy profile look like? We have energy on this side, and we have reaction coordinate. And what we're going to recognize here is that the reactants have a lower energy than the products. So the energy graph profile is going to look like that. Now notice here, the delta H value is going to be between there and there. It's always between those two. And remember what we've said, that delta H is going to be the energy of the product minus the energy of the reactant. And if you read off the value over here, you can see that the product here is going to have a higher value. So that's a higher value. And if we subtract from a higher value the lower value for the reactant, you're going to get a positive. And this is an endothermic reaction. Why? Because you need more activation energy and less energy is released. That energy released is small compared to the activation energy. So the reaction takes in energy, it doesn't give it out. With an exothermic reaction, exit, gives out. So you need to make those links and make sure that you've got it all sorted out. Let's move on to the next question, the next part of this question. And they've asked the question about what is meant by the term activation energy. Really important that you don't get confused between activation energy, the EA, and the delta H. Activation energy is the energy required to start a reaction. Now, you might be saying, but how does that work? Well, let's think of a practical example. We know that, for example, something like paper burns very easily. But we know that at room temperature, paper can sit on the desk and it can sit around the house and it's not suddenly going to start burning. But if we had to put paper into a very high energy environment where the temperature was high, it would immediately start burning. So what we recognize is this activation energy is an energy barrier. It prevents reactions happening, and as we increase the temperature, we can get a reaction going. So the energy comes from the environment. We have to put something in. So you can have a piece of magnesium ribbon lying out in oxygen. It's going to tarnish a little bit. But if you put it into a Bunsen flame and just give it a spark of energy, that's the activation energy. It will burst into this brilliant white flame. That's what we're saying, activation energy. It's the energy that is required to get the molecules of the reactants combining in a way so that there are successful products formed. In that process, they are either absorbing energy or releasing energy, and we have to tell what the difference is. They will absorb some energy and they will release some energy. Which is more, which is less, tells you whether it's an exo or endothermic reaction. Okay, let's move on. Next part, it says, this is a very good question and it's very critical that we understand it. It says, from the information that we've been given, deduce. So we've got to make some prediction. We've got to gather that information, process it, analyze it, make some statement about it, about the rate of the reaction. And we've got to explain, and it's the reactions. So for reaction A, what can we say about the reaction rate? Now, there are many factors that influence reaction rate. We know what some of those factors are. Is there a catalyst present? What are the concentrations of the substances? None of that information is given. What is the temperature given? So what we're going to have to assume is that everything is of the same nature. If we're comparing reactant A, reaction A and reaction B, let's make some assumptions that the particle size, the concentration, and the temperature of the environment is all the same. Once we've made those, then it's a fair test to start to compare which one may have a bigger or slower reaction. Now, we don't know about concentration. We're not going to interpret anything about it. The critical information that we're going to use here is around energy, because they've given us energy. And if they give us energy, we need to think about temperature. So what are we told? We're told that the activation energy over here for part A is 350 kilojoules per mole. 350 kilojoules per mole. And what does that mean? It means that this is a small amount of energy compared to reaction B. For reaction B, the activation energy, if you take a look, is 600 kilojoules per mole. So I've extracted the important information. Now, if we've got a small activation energy at a particular temperature, and you've got a large activation energy, almost double the activation energy, at the same temperature, the reactants are all at the same, otherwise it wouldn't be a fair test, then what can you say? Well, we remember that temperature is the average kinetic energy of molecules, of the reactants and the that are in the system, the whole system. So what we need to recognize is that for a low activation energy, there will be more reactant molecules that will have the specific activation energy. So it's likely that we're going to get more molecules here, more molecules will have the activation energy, or greater than, or more. Than in here, we'll have less molecules with the activation energy or more. As long as a molecule has the activation energy, it can combine with another molecule and form a product. So what we're recognizing here, because the activation energy is less, the chances of a reaction, a collision proceeding successfully is greater. So what I'm going to conclude over here, if the temperature is all the same, then we can expect more successful collisions. And if we get more successful collisions, then that means a higher rate of reaction. Compared to here, where you're going to get less successful collisions, and that means that you're going to have a lower rate of reaction. But guys, really the important thing here is on this question, we need to understand that it's because the temperature is the same. If they were at different temperatures, we couldn't say much about the reaction rate, but we're going to assume that at the same temperature, that reaction A would probably have a higher rate of reaction than reaction B because it has a lower activation energy. Hope I've explained that and that you've followed the reasoning behind it. Okay, so last part of this question says to us, what can be done to reduce the amount of activation energy needed in a reaction? Now, guys, this is pure theory. You really need to know this. Doesn't matter whether it's endothermic or exothermic. The easiest way to remind ourselves is, again, to look at an energy profile. And I'm just going to draw one typical profile, make it something that is slightly endothermic. Let's just make it definitely endothermic. In an energy profile like that, you'd recognize you've got a activation energy, the energy that's required to be put in over there, quite a high activation energy. Now we want to know how we can reduce it. We want to add something to this system. And if we add a catalyst, then the profile will change like that. The activation energy is now less. And that's exactly what we want to be able to show. The activation energy for a catalyst is now less. That's the activation with a catalyst. And that's the answer. How are we going to make sure that we reduce the amount of activation? The only way is to provide a catalyst. Catalyst usually works on the purpose of a surface. You put something there, the catalyst gets involved, it's not used up. It remains as a substance. You start with a certain amount of it at the beginning. At the end of the reaction, the same amount will still be there. So really important that you understand both the mechanism and what a catalyst does. Catalyst speeds up the reaction by reducing the amount of activation energy required. Okay, well, I think it's time for a short break. We've covered energy and energy profiles and made sure that we've got a clear understanding of exo and endothermic. We're going to a break now. After the break, we'll look at another question where we'll look at some investigation type questions. See you after the break.